Second half of today's meetings. So I'm going to be introducing James McGree. He's Associate Professor at QUT, which is in Australia, and he's going to be talking about basic designs for models with interactive light. Take it away, James.
Thanks, Anthony, and thanks to the organisers of MSG. It's great to give a talk here. So as Anthony said, I'm going to talk a bit about design for models with intractable likelihoods, and this is joint work with a PhD student at QUT, so Mahasen, and also a senior lecturer at QUT, Chris Giovandi. Right, so this is an outline of the talk, so it shows where we're going and how we'll get there. So I'll start off by talking about the motivation for this work, the types of models we'll consider, types of experiments, etc. Give a brief background on Bayesian design, because I wasn't sure what the background of the audience was. So I've got a few slides on that. And a particular focus of that will be for models with intractable likelihoods. We'll then move on to talk about utility functions, and again, we have a particular focus on the total entropy utility. Then look at an inference framework called synthetic likelihood, and then look at how we'll approximate our utility functions in this inference framework. Then look briefly at how to locate Bayesian designs. So this is not the focus of the talk, but I thought I should have at least one slide on optimization. So that's in there. We'll then move on to an illustrative example, which is quite useful, just looking at how our approach works in sort of known problems. Then look at the more complicated motivating example, and conclude with a discussion of the work and possibly some future avenues for research. Right, so the motivating example for this work is a disease called foot and mouth disease. It's highly contagious viral disease, and it affects things like cattle, pigs, and sheep. And so there have been outbreaks of foot and mouth disease in the UK in 2001, 2007, in China, in Japan, and other countries as well. And it's actually a pretty nasty sort of disease. So if you Google photos of animals who have this disease, then you find photos of animals with like mouth ulcers in other parts of their body. It looks quite painful. And actually, to try and stop the spread of the disease, there's been mass cullings of these animals. So there's an impact on animal welfare when this disease is out and about. But there's also a large economic impact on these countries, because there are trade restrictions when this disease is spreading. And it's actually quite interesting, because when you look at the literature about how to model the spread of this disease, there are competing models. So some authors came up with what's called an SIR model. Some other authors have come up with an SEIR model. So if we're thinking about designing an experiment for foot and mouth disease, then it might be quite useful to figure out a preferred model here. Should we look at the SIR model, or the data support the SEIR model? I'll talk more about what these models actually are in a moment. So that seems like a fair enough experimental goal if we were to do an experiment. But obviously, once we identify the preferred model, then we'd like to estimate the parameters in that model as well as possible. So we've got two experimental goals, which are model discrimination and parameter estimation. So that motivates our utility function called total entropy, which I'll talk more about as well. So here's a plot of the output of an SEIR model. So what are these models? Well, they're stochastic process models, and you can see 4 lines on these plots. So those 4 lines relate to different states. In this case, pigs can be in at any point in time, and they can change states. So there are 4 states: susceptible, exposed, infectious, and recovered. And this refers to different stages of the disease spread. So for example, if they're in the recovered stage, they've had the disease and they've recovered from that disease. So initially at the start of the experiment, for example, you have lots of susceptibles who may get the disease, and you'll have a few infectious pigs. Okay? You need to have at least one, right? Otherwise nothing will happen. But the model that we'll look at is basically these pigs will transition in general from susceptible to exposed, so they're being exposed to the disease but they're not infectious. Then from exposed they'll become infectious, and then they'll eventually recover. So the dynamics don't necessarily have to follow that. This second plot shows some quite different dynamics, and indeed, for example, the number of recovered goes up and down towards the end. So we're not restricting ourselves for any purpose to the dynamics on the left. It's just the way they turned out once we looked at the data. Okay. But these are the types of models. So what's the design question here? Well, the design question is when to observe this process. So it's not really practical to continuously observe these pigs. You know, people go to sleep and things like that, but also you can't really tell if a pig's been exposed and when they switch to being infectious and things like that. So you probably have to do some lab work, collect some samples and all that sort of stuff. So it's quite expensive to collect data here. And, you know, probably collecting blood samples from 50 pigs would be a nightmare to do. So you'd want to do that as little as possible, I think. So this is the Bayesian design question that we'll try and answer today. And we're being Bayesian because due to the availability of particular utility functions. So, for example, total entropy is available to us in the Bayesian framework. And also because of how we can handle uncertainty in this framework, and in particular model uncertainty. Okay? So what does that mean? Well, it means Bayesian inference will be performed upon obtaining the data, but also in finding the design. So that might seem obvious, but it's not always the case. So in doing that, we have particular challenges that I'll talk about. Right, so some background in design. So as I see it, anyway, there are two main challenges in Bayesian design. And the first is, well, not the first, but a challenge is approximating the expected utility. And we'll see why that is so in a moment. And the second is maximizing this utility. So the focus of this talk is on point one. But as I describe why that is a challenge, then you should see why point two is a challenge as well. So the general aim of Bayesian design is to find D star, where D star maximizes some utility function U. And you can see the expression for U there. And U is some measure of information which we expect to gain from the experiment. So you can see we're basically just integrating out the uncertainty in the model. So we have a set of models here. We assume the M-closed perspective of Bernardo and Smith. So we have K models, and we think at least one of those will be preferred. Then we also have uncertainty due to the data we might observe, so we need to integrate that out. And once we do both of those things, then we calculate our expected utility. So unfortunately, evaluating this utility, well, we can't solve that integral analytically, typically, so we need to do some sort of approximation. The easiest thing to do, I think, is Monte Carlo integration, where basically you sample from your prior and your parameters for each model. So sample your thetas here, and then given those thetas, you sample some y's. And then given those y's, you evaluate your utility a large number of times, capital B, and then you do that for each model, capital K. So a typical utility function is called the Kullback-Leibler distance between the prior and posterior. So what that means, to evaluate this approximation, we need to evaluate capital B times by K posteriors, or we need to sample from them or approximate them, whatever. So this is computationally intensive, and one of the reasons why point one is a major challenge in Bayesian design. It's even more challenging when we can't evaluate the likelihood, and this is the case which we'll consider today. So some background in Bayesian design for models with intractable likelihoods. So this is by no means an exhaustive list. Indeed, I've handpicked these for a particular reason. I'll talk about that now. So Chris and Tony in 2013 used ABC rejection with the Muller algorithm to find designs based on posterior precision. So they maximized posterior precision of the ABC posterior. So using ABC rejection is actually quite easy, well, relatively easy to find a posterior distribution, an ABC posterior, and then based on that you can straightforwardly calculate summary statistics. So the inference algorithm there was selected because it was straightforward to find quantities in the utility function. Okay? Similarly, in the work of Mahasen, he used ABC rejection to find designs for discrimination. So this MI stands for mutual information, and there's a 0, 1 utility function in there. But both of those use the posterior model probability in evaluating the utility. And actually, using ABC rejection, it's straightforward to get an estimate of a posterior model probability as well. So it's the same case here. The inference algorithm was selected because they wanted to use a particular utility function. So obviously, in using ABC rejection, there is a limited number of functions that can be considered. And hopefully, after the work we talk about today, this won't be a limitation anymore. We'll be able to estimate a wide range of utility functions. So it hopefully is quite useful. So before we talk about the utility functions, in order to understand them, we need to understand entropy. So I've got a quick slide here on what entropy is. So if we suppose we've got two discrete random variables, x and y, we can define the entropy of x as h, and it's a negative over the sum of all possible values of x, the probability of x times by the log of the probability of x. Okay? So if we think about prior model probabilities, then we have two models, and if the prior model probabilities are 1/2 and 1/2, then that's the maximum uncertainty or entropy we can have. If we collect some data and the posterior model probabilities become 0.1 and 0.9, then there's less entropy in that random variable. Okay? So we can also define conditional entropy as shown here. And this, so when x and y share some association, then knowing y will give you some information about x. So that's why we look at conditional entropy. So when you take the difference of these two, that's called the mutual information between x and y. And so why is this relevant to design? Well, we actually use this mutual information to define or derive utility functions. Okay? So if we think about x as being a random variable in design, well, that could be a random variable about our parameters, or it could be a random variable about our model indicator. So then y, in that case, will be our data. So given we've observed our data, what have we learned about our model indicator? What have we learned about our parameters? So that's how we can derive utility functions using entropy. So I guess obviously we want to maximize the mutual information, and I guess the last thing I should say is we have some control over y through our design. Okay. So Borth in 1975 defined total entropy just to be the sum of the entropy about the model indicator, m. So m is the random variable denoting the model indicator, and the entropy about the parameters. Okay? And this formula looks pretty simple, but it comes about due to the additivity of entropy. And one thing you may know is that Box and Hill derived expressions for the entropy about the model indicator, and Shannon gave an expression for the entropy about the parameters over a number of models. So we can calculate now in principle, the total entropy about our model indicator, about our parameters, and potentially we can use that as a utility in design. One thing I should say about total entropy is that given we're just summing across these two entropies, there's no real need to weight particular objectives. So we don't need to pre-specify some weight saying emphasize the design on estimation as opposed to discrimination. It's sort of natural in how much we know a priori about each of the random variables. So that's kind of nice. So if you work through some maths, then you find an expression for total entropy as shown here. And so let's not forget that this is our UDYM, which means we need to evaluate this capital B times capital K times. So let's keep that in mind. If we look at this expression, well, if we look at the last term, I mean that seems quite difficult to evaluate. It's the density or probability of y given d. That seems hard. If we look at this first term, that's the posterior, so we need to do that capital K times capital B times. So that seems pretty difficult. And in our case, actually, even just evaluating the likelihood is difficult. Okay. So there are a number of challenges there. And actually, in general, total entropy, I guess as you can see, is a computationally difficult utility to use. So since it was proposed by Borth in 1975, I haven't found anyone who's used it, okay, in the literature. And I think that's why. I think it works, but I think it hasn't been used because it's just difficult to calculate. Okay? Oh yeah, so there are other utilities as well that we could consider, which are actually components of total entropy. So the usual KLD utility, it's quite difficult to calculate as well. So you've got the first term in total entropy here, and you've got the log marginal likelihood there. So that's even when you know the likelihood, that's quite difficult to evaluate a large number of times. And if you look at the model discrimination utility, then it's the log of the posterior model probabilities. Okay, so more difficulties there. But hopefully, with the synthetic likelihood approach that I'll talk about in a moment, we'll be able to estimate not only the total entropy utility, but also these other utilities as well. I mean, they seem obvious because they're components of total entropy, but I just thought I'd make the point. Right, so the synthetic likelihood approach. So back in 2010, Wood proposed this method in a paper which appears in Nature, and he was interested in maximizing the synthetic likelihood. So what he was interested in is approximating the likelihood of y given a parameter value figure. Okay? So the way he did this is he generated a bunch of data sets from the likelihood. So given theta, we generate data set 1, data set 2, data set 3, etc. So obviously we need to be able to, despite not being able to evaluate the likelihood, it must be quite easy to simulate data from the likelihood. Okay? So with our stochastic process models, we can use the Gillespie algorithm to do that quite easily, which is kind of nice. So once we've simulated a large number of data sets, then we calculate summary statistics for each of those data sets. And then we assume those summary statistics follow a normal distribution, multivariate normal. And so we estimate the mean in the variance covariance matrix, and we then evaluate those summary statistics for our observed data and plug all that into the multivariate normal likelihood and evaluate the likelihood. Okay? So Wood maximize this synthetic likelihood to give an estimate for theta. In our case, we'll be using it within a Bayesian framework for a similar purpose, right? We just need an estimate of our likelihood so that we can do our estimates of the utility function. Okay? So in our case, we have count data, and we don't have many counts, actually. So in the examples that we'll consider, we'll have experiments where we'll observe 1, 2, 3, and 4 data points. So there's no real need for summary statistics. So if we go back one, then we don't need this step. And so what we do is we just evaluate the mean variance covariance matrix of our data sets. Okay? But of course, because we have counts, then we need to do something a bit different to evaluate the likelihood of those counts. And basically all we do is we just discretize the multivariate normal distribution. So if I was trying to find the likelihood of 2 counts, which may be 1 and 4, I calculate the probability based on this multivariate normal distribution of the first observation being between 1/2 and 1.5, The second observation being between 3.5 and 4.5, and that's it. Okay. So there are probably more obvious choices for in place of this multivariate normal distribution, and we tried some of those, and I'll talk about that later. Okay. But this is how we approximate the likelihood in these intractable model settings, intractable likelihood settings. But once we have that approximation, it's quite nice because we can estimate other things. So we can estimate the marginal likelihood. So we can just find, if we could sample from a posterior, have independent samples from the posterior, then we can estimate the marginal likelihood of a given model. Once we have that, we can estimate the probability of y given d. And then once we have those two, we can estimate posterior model probabilities. Okay? So once we have this approximation to the likelihood, then we're away. We can evaluate all of our utilities. Or, I think it's a couple of slides. We can evaluate all of our utilities and actually do design. So the last thing I need to talk about is how to approximate the posterior distribution in our case. So because we're only considering cases where we're observing 1, 2, 3, and 4 data points, there's probably not going to be a large jump between the prior and the posterior. So what that means is we could probably do importance sampling with the prior as the importance distribution, and it'll probably be quite efficient. So that's all we do. And so, I mean, if you're familiar with importance sampling, then you know what's going on. But basically, we just sample from the prior, and those samples will all have equal weight. Then we reweight those particles based on the likelihood. And in this case, it's the synthetic likelihood. Okay? So in the end, we'll have a weighted sample from the posterior distribution. Okay? So once we have that, then we can approximate our utilities. Now, the main one we'll focus on is total entropy that's given there. And all we've done is just substitute in our approximations. Okay? So this is a bit of an outline. It's meant to sort of demonstrate that we're not really talking about anything too complicated. We're just doing importance sampling where we've approximated the likelihood via a synthetic likelihood approach. So as we saw at the start, we need to approximate UD, and we do that via Monte Carlo integration. So we simulate a bunch of thetas from the prior, generate a bunch of data sets given those thetas. For each of those YMBs, we need to evaluate our UDYM. So we do that via importance sampling. So to do that, we need approximation to the likelihood, which we get through our synthetic likelihood approach. So once we have that, then we get our weighted sample from the posterior, and then we can approximate our UDYM as shown on the previous slide. So we're not doing anything too complicated. Right, locating design. So one slide on this, because I didn't really want to talk about it too much, but if you look in the literature, there are various different approaches. So for example, there's exhaustive searches, particularly in discrete settings or sequential settings where there aren't too many options. Others have used the Muller algorithm in low-dimensional problems. Anthony and Dave proposed the coordinate exchange algorithm, and they've looked at really quite high-dimensional design problems. Seems to work quite well. But what we use is we call the refined coordinate exchange algorithm, and basically it's just an exchange algorithm where we start with a coarser discrete points in our continuous space, and this space slowly gets reduced and more refined as we go along. So at each iteration, the design space sort of shrinks and gets finer as well. Okay? So the reason why we used this approach is because we wanted to take advantage of the fact that we've pre-simulated all of our data. So we pre-simulated our data so that we could evaluate our utilities in a computationally efficient way. So given we pre-simulated our data, we needed a discrete search algorithm, and we wanted to minimize the number of utility evaluations. So the refined coordinate exchange algorithms seem to do that well. I mean, we've looked at design problems of 15 dimensions and benchmarked it against other algorithms, and it located highly efficient designs with a small number of utility evaluations. Okay? So that's it on optimization. So I think now we'll look at examples. Right. So the first example is, I guess, a simple example where we look at designing for, based on the total entropy utility for the depth model and the SI model. So in this experiment, we'll assume that pigs are either susceptible or they're infected. So there's only two states. And the difference between these two models is basically in this term here. So delta sub t is some small time step, and these probabilities are transition probabilities. So probability of getting one less susceptible in a little tiny time step is given by this formula here. So that's the depth model, and B is the parameter we want to estimate, and S is the number of susceptibles in the experiment. So the SI model is a bit different because of this term here. So this probability now depends on the number of actual infecteds in the experiment. Okay? So the reason why we chose this as our illustrative example is that with the depth model, we can evaluate the likelihood. That's straightforward. And with a bit of effort, so if we follow the work of Cook, Gibson, and Gilligan in 2008, we can do the same for the SI model as well. So what we'll do is we'll design, we'll evaluate some utilities under sort of the truth and compare our synthetic likelihood approach to those utilities. So here's the prior predictive plot of the depth model and the SI model. So I have this up. So this is the median and the 95% credible intervals. So it's probably a bit hard to see, but the main thing I wanted to focus on is the medians. And I wanted to show this because I wanted to show that we didn't make it an easy discrimination problem. We actually tried to make it difficult, as in we tried to make the prior predictive distributions, or at least the medians, pretty similar. Okay, so there you go. Right, so in order to look at our approximation, we generated 500 random designs, then evaluated the total entropy utility, and actually the two other utilities, so the mutual information and the KLD, under the truth and under our approximation. So the truth is where we know the likelihood. We still have Monte Carlo error, we still need to do Monte Carlo integration, but the difference is we can't evaluate the likelihood. So if you look at the first row is mutual information for model discrimination, and if you recall, it's the log of the posterior model probabilities. So in this case, things look great. I was amazed by this plot. So there's basically a linear relationship between the two, and actually the scale is bang on as well. So using this synthetic likelihood approach, we can actually estimate posterior model probabilities, for this case, quite well. If we look at the second row, this is KLD. Things, don't look as great here. You can see that on the x-axis is our approximation, and on the y-axis is the truth. And you can see that we're overestimating our utility, basically, the KLD utility. But that actually doesn't matter, right? All we care about is being able to rank our designs with respect to the utility. So you can see here that efficient designs are still efficient under our approximation, and poor designs are still poor under our approximation. So we're happy with those plots. And the last row is for total entropy, and it's a similar case, right? We're biasedly estimating our utility, but the rankings are essentially fine, so we're happy with that. Okay. So we found some designs, our 1, 2, 3, and 4 point designs. And I don't really know what to say when I look at designs, but if we look at our mutual information utility, then it says, well, this should be the best one-point design for model discrimination. So 0.4. So if we look at our prior predictive, that's like down here somewhere. Okay? And don't know why I'd go down there, but there is quite a big difference between the credible intervals down there. So maybe that's why I decided to go there. And if you look at where the estimation design is, well, it's around 2, and total entropy is sort of somewhere in the middle. Okay? Don't really have anything else insightful to say, but there you go, they're designs. So we may as well evaluate the discrimination and estimation properties of our designs. So here we've generated 500 data sets from each of the designs and evaluated the posterior model probability of the true model. And in this case, the true model is the death model. And we've also got a benchmark against a bunch of random designs. Okay? So you can see, well, in these 3 plots, there's one line that's different, and that's the random design. Pardon me. And the other 3 look quite similar. Okay? So I didn't explain what this plot is, did I? So this is the empirical cumulative distribution of the 500 posterior model probabilities. So basically what we want in an ideal situation is this line staying at 0 density all the way till close to 1 and then sharply rising. Okay? So if we look at the 1-point case, the best design is obviously the mutual information for model discrimination. Then the second best is total entropy, third best is KLD, and lastly the random design. Okay? So the ordering seems sensible, but when we get to 2 or more design points, then you can use any of the 3 utilities for discrimination. It doesn't really matter. When the SI model is true, we see similar things, but there are differences when there are 2 points, 2 design points. So, once we go to 3 and 4, then any of the 3 utility functions would be fine to use. If we look at estimation, so we've plotted here the log of one undeterminate of the variance-covariance matrix against our different designs here. So 1-point designs, 2, 3, and 4. And then we've got KLD, total entropy, mutual information, and the random design. So I guess the first point is that the y-axis isn't KLD. It's it's a component of KLD actually. So the ordering may not be perfect because of that, but certainly the ordering for the 1-point designs seems sensible. We've got KLD, total entropy, mutual information from model discrimination, and the random design. And beyond that, it doesn't matter. You just use any of the designs found based on the utility and get similar results. Right, so move on to the actual motivating example. And here I'm going to talk about, so if you remember, it was the foot and mouth disease, and there are 2 competing models. So the SI model and the SEIR model. So first describe the SEIR model, and basically there are 3 states: susceptibles, infecteds, and recovereds. So we just have 2 probabilities here. So this is the probability of going from a susceptible, reducing the number of susceptibles by 1 and increasing the number of infecteds by 1. And so you can see we've got a parameter here, beta, the number of susceptibles, number of infecteds divided by the total number in the experiment. And similarly, an infectious individual recovers with this probability. So S stays the same, but I gets reduced by 1. And we've got a parameter here, number of infecteds, and times by this really small time step. Okay? If you look at the SEIR model, this model assumes that there's sort of a latent time period where once a pig is exposed to the disease, there's a bit of time before they become infectious. So these are how the probabilities defined in this model, and it's quite similar, but now we've got this, the susceptibles go to exposed, the exposed go to infectious, and the infectious recover. Okay, it's always that sort of pattern. But this model now has 3 parameters, so beta, alpha I, and alpha R. So here's a prior predictive plot as well. So we took these priors from this paper by Baker, and then simulated some data from this model and fit the SIR model. Okay? And again, we tried to make these prior predictives quite similar, so the discrimination problem was challenging. Okay? So in this left plot, we've got a number of infectious individuals, and you can see it goes up and down, and here we've got the number of recovered individuals. So that just increases through time. So here's some designs. KLD, mutual information, and total entropy. So the utilities increase as the number of design points increases. That's reassuring. Good sanity check. You can see total entropy is quite similar to the KLD, at least in the 1-point design, and probably in the 2. If we look at mutual information for model discrimination, it's around 1 day after starting. So again, that's quite early, somewhere around here and here. I kind of expected it to be maybe a bit later, but there you go, it's quite early. Again, that's about all I can say about the designs. Here are the empirical cumulative density plots. Same as before, we want all these to be basically 0 along the x-axis and a sharp rise towards the end. The best design is mutual information for model discrimination, as we would expect, and the ordering is sensible. So it then goes to total entropy. Then the KLD and the random design are pretty similar. I guess the difference in this case is that there's still differences between the performance of these utilities up to 4 design points. So there's still value in using, say, the mutual information for model discrimination, if that's what you're interested in. But in particular, there's still value in using the total entropy utility to do both objectives. Well, we've just seen the one, but if we look at our plots, then there's certainly value in using total entropy. So we can see that the estimation performance is really quite similar between KLD and total entropy. Whereas if we look at the discrimination performance, when the SI model is true, then there's a bit of a difference. Okay? And this continues as we increase the number of design points. So these are the plots for when the SEIR model is generating data. Less differences between the utilities. It's still sort of there, I guess, but you can't see it as much. Right, so to sum up, well, hopefully we've derived or proposed an approach to design experiments for models with intractable likelihoods. I think it's flexible enough in that we can handle a variety of utility functions. I mean, we've just demonstrated three main utility functions in Bayesian design. Total entropy seemed quite useful in the illustrative example when we're considering maybe 1, 2 design points, but beyond that, you could do KLD or mutual information for model discrimination. But there's certainly seen value in using total entropy in the second example. Further work, well, if we think about what we've done, we've basically fitted a normal distribution to the distribution of our data, okay? And our data account data. So it's worthwhile thinking about whether this is appropriate, particularly at the boundaries, where there's probably not much variability. So we did try other, what you think might be more sensible choices. But what we really need to do is come up with like a multivariate binomial or a multivariate Poisson potentially. So we tried a binomial distribution where it's just independent for each of the time points, and our plots of proximate versus true utility, they just look terrible. So didn't bother with that. And you know, when we looked at the normal approximation, it seemed quite reasonable, and the boundaries didn't seem to be a problem either. So, but in saying that, there's probably better choices that could be used. We also need to think about sample size, so the number of pigs. The normal approximation would fall over if there are a small number of pigs. So we looked at typical sort of sample sizes for these trials, and typical size was 25, and we ran our approximation where we assumed 25 pigs, and we got similar results. So we're quite happy with that. You know, I'm not sure you'd want to go too much smaller than that in the design of experiment if you're looking at the spread of this disease, but you know, people might. Okay. We're also interested in whether there are actually any high-dimensional design problems for models with intractable likelihoods. Because if so, I'd be really interested, because I think we could extend this methodology to handle that. And one straightforward way to do that would be to keep the exact same framework, but instead of having the importance distribution as the prior, have a more sensible choice. So you could think about various choices. For example, you may look at maximizing or finding the mode of the synthetic likelihood times by the prior, and maybe looking at the variance covariance around that and inflating that and proposing parameters from that. Okay? So I'm pretty keen to try that, but I can't find any design problems that are high dimensional for models within computationally intractable likelihoods. So if anyone has any, please let me know, because I'd be keen to consider them. Right, so that's it, and there are some references. References, and thank you for listening.
Any questions for James?
So I don't think I quite got what the data would consist of. Is it the sizes of each of your individual compartments? You know, susceptibles, vectors, and curves?
So for the second example, it would be the number of infecteds and the number of recovereds. And for the first example, it's either.
So does that mean that when you construct a design, you say to find something out of these time points, does that mean you have to do a census each time?
Yes. Yeah.
So could you look at whether you can take a sample, whether that's good enough, and how the sample it's not really high dimension.
So do you mean instead of doing all 100 pigs, do 50 of them?
Time 10, take 10 or 50 or 100 and what's the optimum number?
Oh yeah, that's a good idea. Yeah.
For a stupid question, I just didn't quite get what advantage you had using synthetic likelihood over ABC.
Basically, you could estimate parts of these utilities. So for KLD, for example, using the synthetic likelihood approach, you can estimate the marginal likelihood. And
You can't get that using ABC.
no, that's right. So, yeah.
So I was just going to follow up on that. In that I get that as an advantage, but then if I looked at what people do in intractable likelihoods just from their fitting models, I reckon nearly everyone's doing ABC. And I'm just wondering, what do you lose by using synthetic likelihood? So again, you gain. I'm wondering if there's anything you lose.
Yeah, so it will basically come.
You said at the end.
Yeah, so yeah, exactly. So if that's not appropriate or reasonably appropriate, then it might fall over. So synthetic likelihood is basically a special case of ABC. And you know, if we have lots of pigs, then it's the normal approximation to the Poisson is probably fine, and even maybe the binomial is probably okay.
I was surprised that novel works so well, because I've looked at some queuing models which are sort of similar, and a lot of these things actually have infinite variance.
Yep.
which makes it very difficult to do any kind of estimation. I don't know, I've applied for the agents and you can't do underlying models.
So we were really worried about the boundaries.
Yeah.
I don't think we did anything special to handle those. Actually.
Another question about the problem. So the disease is really infectious.
Mm-hmm.
So I mean, is there a risk that when you go out and conduct a census that you might spread the disease? Is
Yeah.
it fair to assume that your active observations actually depend on that?
Probably. Yeah.
I don't know what to do about that.
Yeah. Yeah. I don't know either.
Yeah, and we did it for sort of market chains, we discretized everything here. But this is not the way it works.
So yeah, we ignore that potential. Yeah.
Just in the previous slide, you said that you had reasonable results. If you could elaborate a little bit on
Yeah. So just basically, all we reproduced this plot for sample size of 25, and we saw similar things in terms of the ordering of the designs being sensible. So good designs were still high utility for the approximation, were still high for the actual values, and we're happy with that.
There's quite a lot of variation, isn't there? You have some designs in the middle block, because 0.3 is huge variety. You might by chance get a design which has 50% efficiency.
Yep. So it's not perfect, but we want to be up in this space anyway, right?
Does it make sense to take some kind of aggregate design?
What does that mean?
So every time you run this, you get a command to different designs. So one might say the best thing is to monitor after 5 years, 10 years. One might say 4 years and 11 years. So how do you know which of those is right?
Yeah, so we would just believe the approximated utility. I mean, it's I don't know what else you can do though. Yeah.
Did you sort of go back and check them? Did you sort of run the designs and
Yeah. So
compare the traces and things?
I wouldn't do that. No. So the way we checked them was we didn't check them for optimality, but we checked them in terms of their performance. So these plots were created for the depth model and the SI model under the true when you can evaluate the likelihood. Okay. So there's no synthetic likelihood approximation in getting these posterior model probabilities. And we just looked at whether there were sensible results between the different utilities, and I don't know how to check whether you've got the optimal.
So you know for the true value or the sort of range of utilities of the designs that you could get are.
What's the true value?
So is the x-axis on the other plots not a real idea of this thing?
Oh, that's these ones.
Yeah.
Yeah.
So if I give you an expected, how do you think that's sorry?
Well, we're going to the
Yeah.
how to have discussions over. Any other questions?
The question came through on Twitter. Is there a contradiction between the fact that the MO designs have the low utility value and the fact that they perform so well compared to the other plots?
Can you say that again?
So if we go to the next slide after this one.
Oh, yeah.
For the MA design, we always have very low utility value. If they're in contradiction to that, that would make it perform well commercially.
Right. So
In that size.
yeah. So it's not the same utility. So in the first four utilities there for the KLD, this is the log of the posterior model probability, so it's always going to be negative, and this is the total entropy. So we didn't evaluate all designs under one utility. There are three utilities there. Yeah. Question on Twitter, that's great.
Any questions? Let's thank James and all the other